This video is brought to you by mywayteaching.com.
So in this particular part, we are going to study about the ideas of motion in especially in ancient Indian science. Okay. Ancient Indian thinkers had arrived at an elaborate system of ideas on motion. Force, the cause of motion, was thought to be of different kinds. Okay, first of all, they thought that the force is the main cause of motion, and force are of different types, like force due to continuous pressure, as the force of wind on a sealing vessel. So you can take this example for this force due to continuous pressure is the first kind of force. So it is of the first kind, as when a potter's rod it strikes the wheel, that is also a similar kind of force. And persistent tendency to move in a straight line or restoration of shape in an elastic body, transmitted force by a string rod. The notion in the Vaseika theory of motion perhaps comes closest to the concept of inertia. So, what are all the things that they have explained here are the different kinds of force according to ancient Indian thinkers. So, it's very close to inertia concept. So, Vega, the tendency to move in a straight line, was thought to be opposed by contact with objects, including atmosphere, a parallel to the ideas of friction and air resistance. So Vega, it is tendency to move in a straight line. As I told, it's very similar to inertia of motion. It was thought to be opposed by the contact with objects. So whenever the object comes in contact, like with atmosphere, so those things will oppose the force of Vega. That is nothing but a force of inertia. And it was correctly summarized that the different kinds of motion, like translational, rotational, and vibrational, of an extended body arise from only the translational motion of its constituent particles. See, a falling leaf in the wind may have downward motion as a whole and also rotational and vibrational motion. But each particle of the leaf at an instant they have only a definite displacement. So there was considerable focus in Indian thought on measurement of motion and units of length and even time. So it was known that the position of a particle in space can be of instantaneous motion, which anticipated the modern motion of instantaneous velocity during differential calculus. So the difference between the wave and the current was clearly understood. A current is a motion of particles of water under gravity and fluidity, while a wave results from the transmission of vibrations of water particles. So, here we basically understood the difference between a current and a wave. So, current is nothing but motion of particles of water under gravity and fluidity. It is motion of particles under water. Okay, motion of particles of a water in a under gravity and fluidity, whereas wave, it results from the transmission of vibrations of water particles. It results from the transmission of vibrations of water particles. So this is the difference between current and wave. Okay. So in the next part we are going to study the Newton's first law of motion. Newton, he built on Galileo's ideas and laid the foundation of mechanics in terms of three laws of motion that go his by name, like that is Newton's first law of motion, Newton's second law of motion, and Newton's third law of motion. So Galileo's law of inertia was a starting point which he formulated as the first law of motion, and the law says every body continues to be in its state of rest or of uniform motion in a straight line unless compelled by some external force to act otherwise. So, this is a Newton's first law basically, which is the starting point of this law is the Galileo's law of inertia. So what it says, so everybody continues to be in its state of rest. You just consider a ball which is on the ground, it is in the state of rest, right? So you just consider this is a body now. So every body continues to be in its state of rest or of uniform motion in a straight line. Now this ball is in no rest, so it continues to be in the same position unless it is compelled by some external force. When someone kicks it, that is the external force which is acting on this ball. So at that time the body changes its position, isn't it? So until then, it continues to remain in its position of rest. So that's what the law says. Every body continues to be in its state of rest or of uniform motion in a straight line unless compelled by some external force to act otherwise. In other words, we can express this first law of motion in this way. If the net external force on a body is zero, its acceleration is zero. Acceleration can be non zero only if there is a net external force on the body. So you are getting this. The first explanation and this we can relate those two, isn't it? Both are same which are expressed in two different ways. So if the next external force on a body is zero, again we can consider the same example of a ball. So if there is no external force which is acting on this body, then the acceleration of this ball will be zero. And acceleration, when it can be non-zero, only when there is an external force acting on it, it continues, it changes its position from rest to motion. At that time it gets some acceleration. So if there is no external force, then the acceleration of the body will be zero. That is what this first law says. Galileo Galilei, he was born in Pisa, Italy in 1564. He was a key figure in the scientific revolution in Europe about 4 centuries ago. Galileo proposed the concept of acceleration. Okay, he is the one who proposed the concept of acceleration. From experiments on motion of bodies on inclined planes or falling freely, he contradicted the Aristotelian notion that a force was required to keep a body in motion, and that heavier bodies fall faster than lighter bodies under gravity. He thus arrived at the law of inertia that was the starting point for the Newton's first law. Galileo's discoveries in astronomy were equally revolutionary. In 1609, he designed his own telescope and used it to make a number of startling observations, mountains, and depressions on the surface of the moon, and dark spots on the sun, the moons of Jupiter, and the phases of Venus. He concluded that the Milky Way derived its luminosity because of a large number of stars not visible to the naked eye. In his masterpiece of scientific reasoning, Dialogue on the Two Chief World Systems, Galileo advocated the heliocentric theory of the solar system proposed by Copernicus, which eventually got universal acceptance. Okay. Heliocentric means sun is at the center, all the planets are revolving around the solar system. With Galileo came a turning point in the very method of scientific inquiry. Science was no longer merely observations of nature and inferences from them. Science meant devising and doing experiments to verify theories. Science meant measurement of quantities and a search for mathematical relations between them. Not undeservingly, many regard Galileo as the father of modern science. So, this was the brief interaction about the contributions made by Galileo for the scientific field. See, from this Newton's first law, we can know two kinds of situations are encountered in the application of this law in practice. For example, we know that the next external force on the object is zero. In some cases, like we can say that if the net external force is zero, then the acceleration must be zero, according to this first law, isn't it? See, for example, a spaceship out in an interstellar space far from all other objects and with all its rockets turned off. Consider the example of spaceship. Okay, which is far from the other objects, and with all its rockets turned off, it has no net external force acting on it. So at that time we can conclude that acceleration must be zero according to the first law of motion. If this spaceship is in motion, then it must continue to move with a uniform velocity. Okay, more often we do not know all the forces to begin with. In that case, if we know that an object is unaccelerated, we can infer from the first law that the net external force on the object must be zero. If the object is unaccelerated, automatically in our mind it comes the next external force acting on that particular object is zero from the first law of motion. So gravity is it's everywhere, isn't it? So for terrestrial phenomena in particular, every object experiences gravitational force due to the earth. All Also, objects in motion generally experience friction, viscous force and all. If even though if object, okay, it can be in rest only, but still there are so many forces acting on it. At that case, what we can say, it is not because there are no forces acting on it, but because the various external forces cancel out and add up to zero net external force. Okay, you just consider one simple example here. A book at rest on the table, that is the case A. You can see here a book is at rest on the table. See, it is subjected to two external force. One is the weight W due to the gravity which is acting downward, and another one is the force due to this table, that is the normal force R. So these two forces are acting on this book, and this R is a self adjusting force. The forces are not quite known fully, but the state of motion is known. Here we can see that the book is at rest. So we don't know completely about the forces which are acting on that book, but we know the state of motion, isn't it? So therefore we can conclude from the first law that the magnitude of R equals that of W. So since it is in rest, external force must be zero. So we can conclude that W is equal to R and it cancels out. There is no external force and the net external force acting on that book is zero. So this is correct reasoning. The correct statement is, since the book is observed to be at rest, the net external force on it must be zero according to the first law. This implies that the normal force R must be equal and opposite to weight W. Okay. Similarly, consider the second case, that is the motion of the car starting from rest, picking up speed and then moving on a smooth straight road with uniform speed. When the car is in stationary, there is no net force acting on it. During pickup, it accelerates, isn't it? So this must happen due to net external force. Note that it has to be an external force because acceleration is non-zero when car picks up. The acceleration of the car cannot be accounted for by any internal force. This might sound surprising, but it's true. The only conceivable external force along the road is the force of friction. It is the frictional force that accelerates the car as a whole. When the car moves with a constant velocity, there is no net external force. When the car is at stationary, at that time external force is zero. When the car picks up, at that time it is acted upon by the frictional force of a road. Okay, again when it moves with a uniform velocity, at that time again the net external force acting on the car is zero. So these are the two simple examples for first law of motion.